Hello everyone, my name is Jianyu. I'm from University of British Columbia. Today I will present our paper Incentive Analysis of Bitcoin NG Revisited. This is a joint work with Ziyu Wang from Beihang University, Fangyu and Chen Feng from UBC. In 2008, Nakamoto invented blockchain, the core novelty behind the digital cryptocurrency Bitcoin. In blockchain, clients' transactions are batched into blocks. Each block includes a hash value of the previous block. Through hash reference, blocks are linked into chain structure. To produce blocks, nodes use proof of work in Bitcoin. Specifically, each block includes a random string, which is also called nonce. By changing the value of nonce, nodes can change the hash value of the whole block. To find a valid block, nodes need to find a valid nonce which make the hash value of the whole block start with a given number of leading zeros. By changing the number of leading zeros, we can change the difficulty of mining blocks. Furthermore, we can control the block interval. The block production process is called mining. The nodes who produce blocks are called miners. In Bitcoin, miners are connected through the peer-to-peer network. Each miner stores all the received block. When a miner finds a new block, it will transmit this block to other nodes. In blockchain, miners always produce blocks on the longest chain. To incentivize miners to participate in block mining, there are two rewards. First, each block included in the longest chain can bring its miner a block reward. Second, each transaction has a fee to encourage miners to include this transaction in their block. Nowadays, miners buy FPGA and even ASIC to do block mining, so it's very important to guarantee fairness. This is, miners should win rewards which are proportional to their computation power. Bitcoin suffers from low throughput. The throughput in Bitcoin is 7 transactions per second, which is much smaller than the throughput in other payment systems like Visa. The low throughput is mainly due to two system parameters, the small block size and the long block interval. Although increasing block size or shortening block interval can increase the system throughput, this will reduce the security level. For example, if we shorten the block interval, there will be more forking blocks. As I said previously, and miners in Bitcoin accept blocks in the longest chain. So the origin block will be eventually abandoned by all miners. These abandoned blocks are a waste of computation power, which will reduce the system security level against the adversary. To address the low throughput, many studies show that we have to redesign the protocol of Bitcoin. Bitcoin NG is among the first and the most influential scalable blockchain protocol. In Bitcoin NG, there are two kinds of new block. The first is key block. Key block is produced by proof of work, which is similar with the block in Bitcoin. The only difference is that the key block in Bitcoin NG do not include any transactions. By contrast, transactions are included in microblocks. When a miner finds a key block, it becomes a leader. It can produce a series of microblocks in order until the next key block is produced. From the figure, we can see that the interval between the key block is 10 minutes, which is the same with that in Bitcoin. But the interval between microblocks is 10 seconds, which is much shorter. This means microblocks can include more transactions. By decoupling leader election with transaction ordering, Bitcoin NG can significantly increase the system's throughput. The coupling idea has inspired a new generation of scalable blockchain protocols. These protocols include BYZ Coin, Prisma, and hybrid consensus. These protocols have better throughput and shorter latency, but the incentive design and analysis of these protocols are not clear. Even when we revisit the incentive analysis of Bitcoin NG, we found the analysis has several limitations. There are two incentive attacks for microblock in Bitcoin NG. The first is the longest chain extension attack. In this attack, the adversary can reject some or all microblock if the previous key block owner is honest. It can mine directly on the last accepted block. This attack is incentivized if the transaction fee in microblock go primarily to the first key block owner. The second attack is transaction inclusion attack. In this attack, the adversary when the adversary finds a key block, it withholds some of its own microblock. This attack is incentivized if transaction fee in microblocks go primarily to the second key block owner. To defend these two attacks, Bitcoin NG relies on the transaction fee distributed rate R. Basically, R fraction of the transaction fee in these microblocks goes to the first key block owner. The left 1 minus R goes to the second key block owner. So one important question is how to compute the suitable value of R. Here I provide a simple case of the longest chain extension attack. Through it, we can see how the previous analysis deal with this question. So here we assume there is an honest key block owner, and it produces a macro block which include a transaction. First, if the adversary follows the protocol and it produces the next key block on this macro block, and if the adversary happens to produce the next key block, it will win 1 minus R fraction of the transaction fee. By contrast, if the adversary rejects this macro block and it mines directly on the previous key block, if the adversary happens to produce the next key block, it will re-include this transaction in its own macro block. So in this case, the adversary will win R fraction of the transaction fee, and the probability for this case is alpha. If the adversary produce the next key block, and it will win the left 1 minus R fraction of the transaction fee here. To defend this attack, we should guarantee the revenue for this attack is lower than the revenue of honest mining. In a similar analysis, we can derive this equation for the transaction inclusion attack. So furthermore, we can derive the bounds for the value of R. So here, actually, I provide a very special case. I assume each key block owner can only produce 1 macro block, and each macro block can only include 1 transaction. Through this special case, we can see the limitation of the previous analysis. So we can say if the adversary re-include the transaction in its own macro block, this transaction will take up all the space. This means the adversary can't include another transaction and win the associated transaction fee. So without considering the transaction size and the capacity of a macro block, we ignore the potential loss when having this attack. In other words, this means we will magnify the harm of these two attacks. So the previous analysis is quite reasonable if the selfish miner just hope to get a higher transaction fee from a single transaction. Yeah, through this case, we can say. But in real world, the adversary hope to get a higher transaction fee from all transactions. This means we have to consider the network capacity. To consider network capacity, we model the key block mining process as a random process. We also consider the generation rate and block size of macro block. Through this model, we can consider the impact of network capacity over these two attacks in the incentive analysis. We consider the revenue for the adversary in a time interval t. In particular, we compute the revenue for the adversary in a long term. This equation shows the bounds for the value of R in our results. And this figure provides a comparison between our results with the previous results. From it, we can see our bounds of R is much better than the bounds of R in the previous studies. This means considering the network capacity will not weaken the security claim of Bitcoin NG. In addition, when alpha is greater than 29% and we can't find a valid R for we can't find a suitable R to guarantee the safety. However, in our results, we can always find a valid R when alpha is smaller than 1/2. Here, alpha denotes the fraction of computation power that is controlled by the adversary. Another limitation of the previous study is that they don't consider K-block selfish mining. As I said previously, K-block in Bitcoin NG is similar with the block in Bitcoin. In Bitcoin, there is a famous attack called selfish mining. The studies of selfish mining show that if the adversary controls more than 23% of computation power, they can always gain more from this attack. So we have the question, what will the results be if we consider both macro block and key block in the incentive attacks? Will the joint considering weaken the security level of Bitcoin NG? To answer this question, we use the Markov decision process model. This table shows the possible states and actions for the attacks. And it also shows the probabilities and the rewards for each state transition. By computing the MDP model, we can get the relative revenue for the adversary. This figure shows the relative revenue for the adversary under different mining power alpha. From the figure, we can see that the threshold of making selfish mining profitable the threshold of making attacks profitable is 23%, which is same with that in Bitcoin. And we can also see that under different reward settings, the revenue for the adversary are slightly different. This figure shows the relative revenue for the adversary when the adversary controls large enough computation power. And this figure shows that if the adversary controls more than 35% of the computation power, it can gain more from Bitcoin NG than the revenue in Bitcoin. This means only when the adversary controls large enough computation power, the security level of Bitcoin NG is slightly lower than the security level of Bitcoin. Thank you. That's all my presentation.